Section 4 is all about logic and proof. It's got a grandiose title, but we're going to see logical statements and we're going to see proofs of logical statements. I'm going to start by showing you some notation for writing down logical statements. I have some in this video, and then I have a separate video, section 4.1, that's all about one particular piece of notation that is quite important. But let's start by looking at some statements. I have a couple on the board here. We've already seen quite a few examples of statements, but maybe you've already seen something like, for all x in the set of real numbers, x squared is greater than or equal to 0, which is the statement that all real numbers square to either positive or 0 numbers. And you might have seen a statement like, there exists numbers x, y and z in the set of natural numbers but not 0, such that x to the power of 2025 plus y to the power of 2025 is equal to z to the power of 2025. And logical statements can be true or false, and it's not always obvious which is which. So that first statement about x squared, maybe you already know that that one is true, that real numbers really do have squares that are positive or 0. The second statement on the board is a special case of Fermat's last theorem, and it was proved false by Andrew Wiles in the 1990s. So special case because it didn't have the numbers 2025 in it when Andrew Wiles proved it in the 1990s. He proved that for all n, with n greater than 2, where n is this number here and here and here in the exponents. So we have examples there of statements. There are some things they have in common. They have phrases like there exist and such that and for all. They have parts setting out what sort of things we're talking about and then making a claim about those things. The thing they don't have in common is their truth. One of them is true and one of them is false. Now obviously as mathematicians we would like to work out when statements are true or false, maybe by building up new statements out of existing statements. So I'm going to show you how to combine things together. I've got to start somewhere, so I'm going to start with and, or, and not. And that sentence has got the word and in it between the words. So if you haven't met it before, then it's going to be quite confusing, I think. But here we go. If P and Q are statements, let's pause here. There's a level of abstraction here where I'm writing capital letter P to mean an entire statement, like the ones we just saw. Condensing it down into a single symbol. That's not a variable or a number or something, or even a set of numbers. It's a statement that might be true or false. So if you like, it's some text that we have to pass and decide whether it's true or false. Or if you prefer, it's just its own object, and it's either equal to T or F. In my truth table that's coming up here, I have cases true and false, which I've labelled T and F. Okay, so P and Q are statements, and then we can make a kind of compound statement out of those. If we claim P and Q, the quote marks here indicating this is one sort of phrase that we're claiming, that's a new statement, which might itself be true or false. And separately, in quote marks, P or Q is a different statement that I could write down for any statements P and Q. I could use the ones on the previous page to make some compound statement that says, either squares of real numbers are positive or 0, or Fermat's last theorem is false. And we can decide whether that compound statement that combines the things together, we can decide whether that itself is true or false. I've tried to lay out all the cases in this table. It's a truth table like the ones we saw in a previous video. The idea here is that on the left, we have all of the possibilities for whether or not P and separately Q are true or false. I have 4 rows to go through all of the possibilities of different cases for whether or not P and Q are true or false. And then on the right, I have the output, whether or not these compound statements are true or false. There's a row for every case, and my definition, I suppose, is that P and Q as a statement is true only in this case down here, and the statement P or Q is true in most cases, except for this one at the top, with two Fs over here, which captures the idea of the words and or, of course. And you'll notice that this is very similar to what we did with union and intersection. I'll talk about that in a moment when we see the notation for this. There's one more that I'd like to show you, and that's not, which is simply true when the original statement was false, and also the other way around. So if I have a statement P, I've only got 2 rows here because there's only 2 cases, since I only have P to talk about. And then the statement not P is a separate statement which is either true or false, depending on whether P was false or true. So it just inverts the truth. If you've done some logic gates, but for a course like computer science or something, at some point in your life, then you might have met logical gates to do all 3 of these things, and you might have met truth tables before to explain what they're doing. But either way, there's my definition. Okay, there's some notation for these, so that I don't have to write the words and, or, and not, and the notation looks like this. So I have this one which means and, this one which means or, and this one which means not. And maybe 2 of these remind you of the notation that we use for intersection and union of sets. So if A and B are sets, then we had notation for the intersection of A and B that looks like this. Now these ones are slightly more rounded symbols than these ones. They are different, but there's a correspondence because if you're talking about an element being in the intersection, then that means that it means both that X is in the set A and X is in the set B. Where this is the new logical and symbol, like this one over here. And for the union, X being an element of the union there means that X is in A or X is in B. And that's this new or symbol. So there is a strong correspondence between intersection, union, and these new symbols and or. If you're talking about the true or false statements, is X an element of when you have these sets. Similarly, this one probably doesn't remind you of the complement of A, but let's just fill out our little table here. X in the complement of A means not X in A. It's a little bit awkward reading these with the word not at the front. I'm not quite sure. Not Fermat's last theorem is quite hard to pronounce in a way, but that's how we write it, so that's how I tend to say it when I'm reading it out. Okay, so that's some notation for these. I would like to show you De Morgan's laws for logic. We've already seen De Morgan's laws for sets, membership of various sets. There's also De Morgan's laws for, let's come back to that, De Morgan's laws for logic, which lay out the idea that you can negate the statement P or Q by writing not P and not Q. In words, this says that you're in neither. Neither are true. Sorry. So instead of saying P or Q, the negation of that, P or Q, very permissive, to negate that, it must be the case that not P and also not Q. And similarly, the negation of P and Q, if it's not the case that both are true, then it must be the case that one of them is false. So not P or not Q. So this says not both in words. And you can write out a proof of this using a truth table. The truth table is extremely similar to the one that we looked at in the video on truth tables. In fact, it's better than that because for the truth tables video, we had the idea that the column labelled A meant X is an element of A, true or false. And the column labelled not A or B meant X is not a member of A or B. It was in the complement of the union of A and B. But now, P is just the name for the statement, which doesn't have to be about membership of a set at all. So our column really can be labelled P just to mean the statement P is either true or false. So good news, you can take the truth tables that we had before and just translate them over here, and it's a more natural setting for those truth tables as well. Okay, I skipped over an example, so let's have a look at this. This is interpreting some symbols. If I have P for the statement n is 2, which is quite a simple statement, and I have Q for the different statement n is even, we're talking about natural numbers here, then P or Q means n is 2 or n is even, which simplifies a bit. And you could write out n is 2 or n is even, but people will give you a funny look. Unjustified funny look, that's a perfectly valid statement. You can simplify that to n is even. You don't have to. There's nothing logically incorrect with the claim n equals 2 or n is even. That's fine. Okay, it's equivalent to the statement n is even. The and example here says if n is 2 and n is even, then, well, that simplifies as well. N is even and also n is 2. Well, I mean, that simplifies to n equals 2. And the statement not P is the statement that n is not 2. There's a symmetry to these first two things between P and Q. So if you check the truth table, then you'll see that swapping P and Q doesn't affect the truth of the statement P and Q. It's this equivalent to Q and P. And also P or Q is equivalent to Q or P. Forwards and backwards, which could be useful if you're rearranging a complicated statement, but it's also how the words and or work in everyday language, so possibly you're already just swapping those things around without consulting any truth tables in your head. Anyway, that's notation for and or and not, which I'd like to use a little bit in the coming videos. There's one more important symbol that I would like to show you, and that's the implication symbol, and that gets its own video. So I'll see you in the next video, which is all about the implies arrow.